Welcome to today's webinar, PFAS 103, Source Zone Treatment, and thank you for taking the time to join us today. I'm Nate Biershank, the Marketing Operations Specialist here at Cascade, and I'll be your moderator for today's broadcast. While we wait for everyone to have a chance to log in and join us, I just want to congratulate Chris D, who's the winner of this webinar's drawing for a free lunch. And just as a reminder, before every webinar, we draw a name from registrants who submitted a question while RSVPing, and then we send them a gift card to enjoy something to eat. So the next time you register for one of our webinars and have a question for our presenters, please be sure to submit it when you register. Chris, please check your inbox for an e-gift card from Uber Eats. I'm happy to introduce you all to today's presenters, but first I must note that Cascade's Vice President of Technology, Elliot Cooper, is unable to participate in today's webinar. If you have any questions for him after the webinar, would like to connect, you can shoot him an email at ecooper@cascade-env.com. Let's see. While we'll miss Elliot, we are pleased to welcome today's presenters, TerraTherm's John LaChance, Vice President of Development, and Steffen Gripeke, Vice President of Technology. John and Steffen will begin their presentations shortly, but before I turn the floor over to them, I've got a few logistics to cover. All attendees are in listen-only mode. At any time during the presentation, however, you can type a question into the question panel, which is going to be found on the right-hand side of your screen. At the end of the presentation, we'll have time to address those questions, as well as any questions that were submitted during registration. And this broadcast is being recorded, and it's going to be posted on the same page that you all registered on for this webinar. And if you're just joining us, welcome to today's webinar, PFAS 103, Source Zone Treatment. We're so glad you're able to join us. If this is your first time attending a Cascade webinar, I want to extend a special welcome. Cascade Environmental is a field services provider that offers drilling, site characterization, and remediation. Everything you need from project concept to completion. Our remediation division has the nation's largest fleet of equipment, the deepest bench of technologies to choose from, and leading industry experts who can help you get the results you need. You can learn from them and connect with many of those experts in our regularly scheduled monthly webinars. Now I'd like to welcome TerraTherm's John LaChance, again, VP of Development, and Steffen Gripeke, Vice President of Technology. We're looking forward to hearing about your insights into PFAS source zone treatment, so I'll let you guys take it away.
Well, thank you very much, Nate, and thank you all for joining us today. I also want to give a big shout out to Allison, who's on our also on our panel today. Sorry, and she is our senior scientist here at TerraTherm, and she's also one of our lead chemists, and she's been integral to our lab scale and PFAS treatment studies. So thank you, Allison, for joining us. So let's get started here. Let's look at our agenda. So for today, we're going to focus on thermal treatment, as Nate said. Elliot unfortunately couldn't make it today, and we were going to talk about sort of Cascade Chemistry's approach as well as thermal treatment. But since he wasn't here today, the timing actually kind of worked out well for us, because we're sitting on some really exciting news in the front of thermal treatment of PFAS. So that allowed us to build out a little bit more of some of the background and what we're seeing relative to lab scale and bench scale studies for treatment of PFAS using thermal techniques. So we're going to share some of that with you today. But first, we're going to talk a little bit about what we're trying to treat. What are PFAS? As you probably know, there's a whole host of compounds, and what some of those treatment options, thermal treatment options, are. And what does actually we mean when we say thermal treatment of PFAS? I think a lot of folks are familiar with excavation and ex situ, say rotary kiln type thermal treatment approaches. We're going to talk a little bit more about what that looks like and kind of the background, where this comes from, where this concept of thermal treatment of PFAS comes from. And as I said before, we're going to share some laboratory studies with you, some results that actually the first round of work we did was a couple of years ago, but we recently completed this summer round 2, which has led us to some interesting results. And then Steffen will pick up with more specific on field scale applications and how we would actually use the information we have on behavior of PFAS at these elevated temperatures to actually design and implement a full-scale application. So what are we trying to treat here? And you've probably seen this figure or something similar. PFAS is per and polyfluoroalkyls or alkyl substances, and it includes a lot of things. A lot of our focus these days are on just a few of these compounds, and you can see some highlighted here that the EPA has recently proposed some cleanup standards for PFOS and PFOA. I also want to point out PFC, perfluorinated compounds, which is now commonly used to describe things like carbon tetrafluoride. These are greenhouse gases, and HFCs, hydrofluorocarbons. And these compounds may not be PFAS, but they're also fluorinated compounds or fluorinated hydrocarbons. And as we'll see as we go through this, they are something that has to be accounted for or tracked when we look at these laboratory studies, the fate of PFAS and when we're heating it up, as well as what we would anticipate, in the field at a full-scale project. So we dive into this a little deeper. You can see these per and polyfluoroalkyl substances are really a whole bunch of different things. And you can kind of look if you Google, you'll find answers to this, like how many PFAS compounds are there? That ranges from 3,000 to 10,000 to more than 10,000 compounds. So there's a lot of particular substances, and it's as we get into this, you'll see that one of the challenges for us, the industry, is looking for, sampling for the different media we're dealing with, soil, the water, the vapor, and being able to analyze for a fraction of these. So, again, the focus is kind of on PFOA and some of the other related perfluoroalkyl acids and PFOS. And so we're going to focus a little bit on these two, as you'll see as we go through here. So PFAS treatment, what do we currently have for options? Well, as you saw in PFAS 102 or plume treatment, what PFAS 102 is kind of the plume treatment approaches. And we have cutoff technologies that can be implemented, whether that's a barrier wall, whether that's a colloidal carbon wall. These technologies are really kind of holding PFAS back. And they should be viewed as kind of quasi-temporary. I mean, they can be enhanced over time, but they're only going to basically work as long as the sorptive material can sorb the PFAS, and then you'll get breakthrough again. There's point of source treatment, such as pump and treat, and there's different means for removing the PFAS from water so it's safe for drinking. And as I mentioned, there's ways of fixating the PFAS in situ using colloidal products, whether in a barrier or in situ soil mixing or just straight up injection. For the source zone itself, I mean, most of the typical kinds of source zone treatment technologies have been applied. Things including excavation, soil washing, or stockpiling and disposal in a landfill, or stabilization. And as I mentioned before, this excavation and high temperature treatment using kind of a rotary kiln approach. What we're going to talk about today is the in situ or ex situ thermal remediation, which is different than putting it through a rotary kiln. So some of the technologies that we have for thermal remediation projects include TCH, ERH, steam, and combinations. And the question is really which of these technologies or which of them can be used for treating PFAS. So when we start, usually when we screen technologies for what's applicable, we first look at the COCs. Are we looking at VOCs? Are we looking at NAPL? When we're looking at PFAS, we're looking at high boiling point compounds. And the mechanisms that we're targeting are volatilization and destruction. So that brings us to an approach that we have to, or a technology that has to be able to heat the subsurface up to 100 degrees C, boil off the water, and then achieve temperatures higher than that to get this volatilization and destruction of these high boiling point compounds. And when we screen out our technologies looking at their capabilities, the only one that can really do that is thermal conduction heating. The other technologies, ERH and steam, are limited to basically 100 degrees C, the boiling point of water. So we take a closer look at thermal conduction heating. What that basically entails is drilling holes in the ground, putting pipe in those boreholes, and then putting heating elements inside those pipes, turn those on, and we get radiant heat flux or thermal conduction of heat and energy away from those heaters out into the formation, and eventually get the formation up to the desired temperature. As we're doing this, we're applying a vacuum. So we're always heating and applying a vacuum to remove the steam and the vapors that are formed in degradation products. And as I mentioned, we could also do this ex situ, the same approach, using thermal conduction heating in piles. And Steffen's going to go into more detail on how we do this. So we have both in situ and ex situ treatment options here available to us. When we look at the thermal literature, what does that tell us about what we can expect for the behavior of these compounds as we heat them up? We have some example PFOS compounds here. You can see vapor pressures at a range of temperatures, and we look at ambient. These things are semi-volatile or very low volatile compounds. We increase the temperature a bit. You can see we see a moderate increase in temperature, but they're difficult to remove if we just heat to 100 degrees C. And you can see that corresponds with their boiling points, which are relatively high compared to VOCs. When we look at thermal degradation, what we see is that we do get breakdown of these compounds, and if we break them out, and again, there's a lot of different classifications of PFAS. When we look at sulfonic acids or carboxylic acids or sulfonic amides, we can see with these broad groups, we can get breakdown or destruction of these compounds at varying temperature ranges, 450 to 500 C for the sulfonic acids, 100 to 150 C for the carboxylic acids, and 150 to 200 C for the sulfonic amides. So this gives us the kind of the basis or the foundation for why thermal remediation is an approach that can be effective here. So let's take a look at what the first laboratory studies we did a couple of years ago showed us and kind of brought us to where we are today. What we like about lab studies is we can control the environment. We know what's in the sand. We have a good way of heating that uniformly, and we can track, what happens, what comes off the material as we heat it up. It also allows us to do a rigorous job of testing analytic methods. So we remove a lot of the field uncertainty associated with sampling and analysis at a full scale. And what we really want to target here is looking at what kind of reductions in the PFAS can we achieve at different temperatures, and also can we provide some insight as to how these components or these compounds are removed. So how is the PFAS removed? Is it via evaporation? So does it volatilize and leave the soil, or is it decomposed in the soil? Is it mineralized in the soil? So this gives you an example of what our lab test setup looks like. We had a soil container that was in a muffle oven, so we could heat it up to various temperatures. We had air coming into it, so we had airflow right through there, which picked up any steam or any contaminant or COCs or degradation products that were formed. Then we sent it through a condenser to knock out the steam during the dry out phase of the soil. That created a condensate, and then the rest of the vapor we sent through a sorbent tube, so we could analyze that for PFAS and degradation products. So what this first round of testing entailed was basically looking at 3 different temperature ranges, 250, 350, and 500 C. And we held those temperatures for each of those tests for 7 days. When we look at a field scale, and Steffen's going to talk about this, we actually will hold these temperatures much longer than this. So this is a little conservative in terms of what our expectations are relative to removal efficiencies. So how do we sort of get our heads around analyzing for greater than 3,000 compounds, right? Well, we have analyses that'll give us target PFAS, whether it's 30 or 35 PFAS compounds. So we can look at those, and we could do that soil and water. And again, what we did for the vapors to sorbent onto sorbent tubes and analyze that. We can also do a total oxidizable precursor assay. What this does is it converts any other fluorinated compounds there, other PFAS compounds that are precursors to the target PFAS that are present there, converts everything, and we get a total, then we analyze it using the same PFAS methods, and we get a total PFAS target compound and precursor compound number. And if we subtract those two, the difference will get us the total precursors. So we can kind of look for the stuff that doesn't typically come out in our PFAS analysis. So things that don't show up on our 30 or 35 target list, we can pick up using TOPA and then subtract that will give us an idea of how many of these precursors that we typically analyze for are there. And we also always look for total inorganic fluorine. So that gives us an idea of what's their background for fluorine or fluoride in the system, as well as what's mineralized after we're done treating. So this gives you an idea of the ramping up of the temperature for the couple of the runs here. You can see the dark green is the temperature of the soil. So we got it up to 350 C and held it there for one, and then for the other one up to 500 C. The light green line is just the heat trace on the vapor tube leaving the and we heat up these target temperatures and hold them for 7 days. So let's take a look at the results. So from this first laboratory analysis that we did, this gives you an idea of the results. What you see here in this first column is the untreated, the starting concentrations, and this particular sample of soil from this particular site was highly contaminated with a range of PFAS, most specifically with PFOS. And when we ran this at 250 C, one of the things you noticed is we didn't really see a whole lot happening. Now this matches up with what we expected on the literature. We really didn't expect much to happen in terms of degradation or in terms of volatilization. So that's what we saw. What's interesting is that bringing it to 350 C, however, we see a significant drop. Basically, the target PFAS compounds were removed. Whether that's removal through volatilization or through degradation, we'll get into that a little bit later. Then we brought it up even higher to 500 C. We see everything basically at non-detect at roughly 5 micrograms per kilogram. You can see similar kinds of results for the other sample from site 2. For the next couple of runs we did on the samples from site 3 and site 4, we had lower starting concentrations, but we also were able to get much lower detection limits. So instead of 5 micrograms per kilogram, we have 0.1 micrograms per kilogram. And when we heat to 400 C for these runs here, you can see we got very good removal, a little bit of PFOS, a very small amount of PFOS at the end. So what did these results indicate? That we can eliminate PFAS from the soil by heating to 350 to 500 C for several days. And we sort of a trade-off here. We can heat to 350, 400 for longer periods, or heat to 500 degrees C for shorter periods. So it's really, when we look at a site, we're looking at what is the optimal target temperature and time at temperature. The fluorine that we saw was fluorine was removed corresponding to PFAS being removed from this soil. So that all made sense for tracking what was happening in the soil. The mechanisms based on this study, what we think is happening there is we were getting both volatilization and degradation based on our soil, water, and vapor samples. And in some cases, we were getting degradation followed by volatilization. So we're getting breakdown of those big, longer chain, higher molecular weight PFAS compounds to smaller compounds, things that we would call precursors, but are degradation products here. And those things would have even a higher vapor pressure and lower boiling point, so they readily volatilize. Unfortunately, our mass balance, we could not quite close that fluorine mass balance, and that's kind of important to really answer some of the key questions about the fate. Like, what happens to the PFAS? Is it just partially broken down? Is it completely broken down? Is it volatilized out of the system? So we had some work to do after this round of work. So that brought us to round 2, which is, again, a lab study we completed last year, or started last year and completed this summer. You can see here what we're doing is, for this test, instead of using natural soil contaminated with PFAS chemicals, we are spiking a known amount, known quantity, known concentration into a known volume. So we know what's going in here. And what we spiked with was PFOS, as I'll talk about in a second here. So this just shows you our rough laboratory setup. Our goals here was to look at if we're getting volatilization of PFAS precursors or other fluorinated compounds, how do we ensure that we're getting effective treatment of that? Effective just in terms of efficiency, but also as from a sustainability perspective. How do we get those PFAS compounds completely treated? So total treatment of PFAS and fluorinated compounds, not just moving them from one phase to another and discharging them to the atmosphere. So we looked at some catalytic treatment options for that and built that into our study. We also wanted to understand and dig more into the fate of PFAS in the system. How much was destroyed or mineralized, what kind of volatilization we were getting, and transformation or degradation of the compounds. And key to this was tracking and trying to close the fluorine mass balance. So could we do that? So this gives you an idea of the bench scale configuration. Similar to what we did before, we had a muffle furnace. This time we had two containers. One was with our catalyst and the other was with our sand soil that's been spiked with PFOS, PFOS. And we heated this to 350 C. Now, when we're using the catalyst, we're heating this to 600 C. What you can see here is the boiling phase, because remember, we're starting with some soil moisture here. Initially, we're heating up to 100 degrees C, and we have to boil off that water. So while we're doing this, we're creating a moist stream. So what we did here is to send it through a condenser and empty it into a condensate impinger. Once we get up to temperature, that's when we start going through, and it's dried, the soil's dried out, and no more steam is being produced. Then we're sending the vapor stream through our catalyst. And instead of condensate here, since it's a dry stream, we're sending it through an alkaline impinger so we can capture anything that might be coming out before we send it to the sorbent vapor tube. And then what we're doing, I'm not going to go into a whole lot of detail on this. That'll be maybe another presentation paper, or Allison, I know, has a poster at the Amherst UMass Soil Conference coming up in October on this. But we're sampling each of these sections of media, the tubes and everything, to get it to be able to track where the PFAS is moving, where the fluorine is ending up in the system. So just in general, what we did was look at PFAS in soil, water, and vapors. For this particular study, we had a 35 target list that Eurofins provided us the analysis for. And since we can't analyze for all of those different PFAS compounds or fluorinated compounds, we also look for fluorine. And we did this by looking at inorganic fluorine as well as using combustion ion chromatography, or CIC, to look at total or both inorganic and organic fluoride or fluorine. And we, if you subtract the total F from CIC, if you subtract fluoride from that, you can actually get a rough idea of maybe what's there as organic. So here's the results from this work. And what you can see here is a couple interesting things. One is this is our starting blank sand, and even the starting blank sand that you buy from the store or Home Depot or Tractor Supply or wherever, you're going to pick up PFAS. This is the forever nature of these forever chemicals. They're around in the environment. So even our blank sand had some low starting concentrations of PFAS. And again, these are micrograms per kilogram levels that we're talking about. This is what we spiked into it. This is the concentration present of PFAS, calculated concentration in the soil after we added our PFAS spike. And then you can see our four separate runs. So these each represent 350 C for 7 days on 4 different times. What's interesting here is that we get very good removal of the PFAS, but we also see a smattering of other PFAS compounds come and go based on these runs. Some are kind of persistent throughout, but others kind of show up and don't show up. This is just the nature of working with PFAS and the complexities of the degradation and sampling and analytical methods, I think, in part what you're seeing. But what's clear here is we're also getting some minor amounts of transformation or degradation into some of these other compounds while we're heating it up. So to summarize what we saw here in terms of these results, we basically had, for all 4 runs, we had an average of 99.5% DRE, and that's at 350 C for 7 days. So what we know is that if we actually heat it up to higher temperatures, we'd expect to even be able to do better than this. So this is great. This shows us that thermal treatment can be effective for removal of PFAS, and we know if we treat it to 400 C for 7 days or 14 days, we can do much better than this, and we can target the treatment to meet the expected remedial cleanup goals. we take a closer look at tracking the fluorine through the system. So what this table is summarizing, and I broke it out in terms of the different steps we had. We had soil, remember, then it went into the catalyst. And while we're steaming, we went into a condenser to knock out the water. After the soil is up to temperatures above 100 degrees C, then we bypass the condenser, go to the impinger, and then we have vapor discharge. So throughout the treatment duration of the run, we're basically collecting any final fluorine or PFAS that moves through the system in this tube. So when we look at this, what you have here is the fluorine. So this is all in fluorine. It's not PFAS or specific compounds. So we're looking at the fluorine from the CIC analysis, which includes inorganic and organic. We have the fluoride, inorganic fluorine. We have the PFAS fluorine, and we looked at this for the different media and different steps in the system. I'm just going to walk through this kind of quickly here to give you an idea of what these results, what the story is, what they kind of tell us happened here. So background, again, very low, but some detectable levels of PFAS or target PFAS list. What's interesting is that the CIC analysis shows that we've got basically 1.1 milligrams of fluorine in that sand that was in the container. And we had very low inorganics. So one way to look at this is that this is some form of organic fluorine that's present in that sand. It doesn't show up as PFAS, but it shows up on the CIC analysis. Well, again, this is our mass of fluorine associated with the PFOS that we spiked in. So this is what we added to the system. And when we look at the total fluorine budget, let's just say, in that sample chamber is about 19.76 milligrams of fluorine. When we look at what's in the catalyst, because remember we sent the vapor streams through the catalyst, we had about 0.22 in the catalyst to start. So let's take a look at where this goes and what happens. What's really interesting, as we saw, the PFAS disappeared, and at the end we only had 0.011. So that's a tremendous, that's your PFAS removal efficiency there. The question is, where does this go? Where does it go in the system, right? Does it volatilize and leave the system? If it does that, it should show up in our sorbent tube. Does it degrade, etc.? So we'll take a closer look at that. So we look at the total that was in the soil to start with, this 19.76. Of that, we see 9.6 still remaining in the soil, but it's just not PFAS at this point. It's some form of inorganic and organic fluorine. We also see some inorganic fluorine, 1.9, almost 2 milligrams of fluorine. So we're definitely getting some mineralization. What's really interesting here is that in the catalyst, we're seeing 10.4. So a big chunk, roughly 50% or 55% of the fluorine that's associated with PFAS in the soil leaves the soil and ends up in the catalyst. That mechanism is volatilization. So it's either straight up volatilization of our target PFAS compounds or their degradation of volatilization. We see very little in the condenser. No surprise there. We kind of didn't expect to see much in the catalyst at 100 degrees C. We also pick up some fluoride in the impinger. This is probably HF that's moving through the system, and this is where we're picking it up in the impinger. What's really important, if you think of this as kind of a typical treatment train with a soil, some sort of thermal catalytic oxidizer, we're seeing very, very, very little of the PFAS, of the fluorine or the PFAS coming out in the vapor stream. So we look at the mass balance. Remember, we had 19.76 total pre, plus this 0.22. That gives us roughly 20 milligrams of fluorine in the system. What we know is that between what's remaining in the soil, 9.16, and what's in the catalyst, nothing in the condenser and a little bit in the impinger, that gets us 22.8. So that's a little bit more than what we estimated to be in there, but this 18.66 was an estimated or calculated number based on a lab certification and then a follow-on lab analysis of it, our own lab analysis of it. So we had kind of modified that a bit. And if you look at what we spiked in, this is what we corrected it to based on our lab analysis. Uncorrected, it would have been roughly 28.3, where we ended up was 22.79. So we effectively closed the mass balance here. What's cool about this is when we looked at where this fluorine ended up in the system, again, roughly 42% in the soil. We accounted for another 46% in the catalyst. This showed up because of volatilization. And then we had some in the alkaline impinger, again, indicating destruction and creation of HF in the system. Very little in the condensate, very little in the vapor tube. We also see, we look at the distribution in the catalyst, we see something similar. We see a lot of this other species, like what is this material here? I'm sorry, this is the soil, not the catalyst. But we dive into what that fluorine, how it appeared in the system. Very little of it is the targeted, obviously. We had some extractable, which we know is mineralized fluorine, but this 79.7%, what is that? Well, we know we ran this at 350 C, so we really don't expect this to be organic fluorine, but it shows up under the CIC analysis. So we're not really sure what that is, and this is really, I think, one of the questions that has to be kind of addressed further and more fully. We think it's some sort of insoluble fluorine complex, shows up as potentially on the CIC, so it could be inorganic, could be organic, but it's something that is, at these temperatures, is probably not a PFAS or precursor compound. We saw something similar in the catalyst, which was even at a higher temperature. We had 98.4% of the fluorine show up as this other species that we're not really sure what it is. Again, we think it's some stable or insoluble fluorine complex based on the temperatures that this catalyst was at. So some key takeaways here. The PFAS can be removed, and we think it's a combination of destruction, mineralization, as well as vaporization, and likely degradation and vaporization as well. We also, these results indicate that catalytic thermal oxidation, so using a thermal oxidizer that incorporates some sort of catalytic media, would be very effective at treating and meeting any sort of stringent vapor emission standards. So that's key. That's a key part. We don't want to just emit some unknown compounds, fluorinated compounds, to the atmosphere. What's really cool for us, and I think for the industry, is we're able to demonstrate another closure of the fluorine mass balance using combustion ion chromatography. So that was satisfying to see, and it helped us to really understand and assure ourselves that we knew what was happening here. And basically, what we think is happening is 45 to 55% of the PFAS fluorine remains in the soil, and it's there either as some sort of insoluble, stable, or inorganic fluorine compound, and we're getting another 45, 55% that leaves the soil via volatilization. And then if you incorporate this kind of approach with a catalytic thermal oxidizer, we can get the remaining that fluorine or that mass of fluorinated compound degraded and destroyed in that catalyst. And I think I just covered this already. We don't think that fluorine that's showing up on the CIC analysis is actual PFAS or other precursor compounds. We think it's a stable mineral-bound insoluble form. So future work should really focus to look on just what is that stuff. Can we do some specific analyses to look at that? And with that, I'm going to turn it over to Steffen to talk about some field scale applications.
Absolutely, yes. Thank you, John. Yeah, so the remaining part of this presentation will focus on what do we use this information for and how will we attack this in the field. So first of all the the thermal projects to date have been focused on laboratory scale. There are some pilot scale and research scale projects out there, but no one has yet done a full-scale PFAS remediation, and the industry is basically not ready for it yet. But we are, or at least we're trying to get ahead of the game here and be ready with the field application as well. And we are basing, the next couple of slides here, we have a few options when it comes to treating PFAS in a bigger scale. First of all, there's a heated box. That's one of our ways of treating smaller volume. We use a heated box for typically up to 1,000 to 1,500, maybe 2,000 cubic yards. And then if we are looking at bigger volumes than that, we would likely default to our IPTD, in-pile thermal desorption technology. So talking about both of them here, jumping it here. Before we get started into the details here, so how many of these ex situ and IPTD projects have we done the past 10 years? Actually, it's the past 7 years. We've done a total of 8 of them. 4 of them has been the heated box application, and the other 4 has been in-pile thermal desorption application. So, as I said again, none of them have been for PFAS, but we utilized this technology already for dioxins, for PAHs, PCBs, and SVOCs in general. So, given that we now know that as long as we reach a temperature of roughly 350 degrees, which we do in all these applications, then we can treat the PFAS. That's basically our approach in the field as well. So if you look at this list down here, we've done the smallest we have done is basically a roughly 30 cubic yard heated box application. Here, that was a project in Denmark, treating mercury and pesticides. And then when we try to focus on the bigger ones, the biggest one we have done is an IPTD application for dioxins in Vietnam, Da Nang Airport, back in 2017. So they come in all different kinds of sizes, definitely, but focusing on the heated box, each of these heated boxes typically hold between 80 and 100 cubic yards of soils. If you have more soil at your site, you may mobilize 2 or 3 or 4 of these and basically switch between the different boxes and then run them simultaneously. Common for all of them is that they need a treatment system, as John alluded to, and that's what you see here in the background in the picture. So looking at a field scale application, if I can go to the next one here. John, can you help me a little bit? Yeah, there you go. This was a heated box we completed 2 years ago in Asia. This was dioxins, 60 cubic yards in this box you see here. The target treatment zone was the treatment temperature was 335 degrees Celsius. So same range as the 350 to 400 that John mentioned before. The heaters in this heated box are dominantly installed in the floor of the heated box and in the side, so the boxes are easy to empty out and reload. And in this pilot, we had 6 temperature monitoring points, and we operated the box for 50 days. And for this pilot, for dioxins, our vapor treatment was basically thermal oxidation. So that's kind of where we took the dioxins and treated them in the thermal oxidizer. And this was a project that was completed by TerraTherm Asia. Looking at the heat up profile for this application, basically the first roughly month of operation, that's what it took us to get up to temperature. So first we got up to 100, we had to boil off the water. In this application, it was actually sludge from a soil washing plant that we treated. So similar to some of the soil washing projects that's going on right now, or that's planned now for PFAS, the sludge or leftover could be treated using this technology. But roughly after a month, we were above the dedicated target treatment zone, the temperature, and at that point, as we basically want to maintain the temperature. It's not all about just reaching the temperature, it's also about duration and resident time. So in this case, we maintained the temperature for 2 to 3 weeks to basically get to the end goal for this particular dioxin project. Just to look at the components here, we have the heated box. In this case, it was put in a little tent. The white boxes to the left in the picture was our power controllers. And then in the background, you see the thermal oxidizer that was basically used to treat the vapors from this heated box. When we're looking at bigger soil piles, we have two, or soil volumes, we have two options. First of all, the IPTD application. This shows a schematic of it. In this case, this figure shows the heaters installed horizontally in the IPTD piles, but we still have a power supply. We still need a treatment system associated with this system. For fixed operations, there are some applications where there's a continuous generation of contaminated soils with either hydrocarbons that could be from the oil industry. This can also be applied basically for the fixed operations, and in that case we would build boxes instead. So basically scale up the heated box concept. So that's what this is showing. But the bottom line is that the piles can basically be designed to the site-specific needs, and this does require the PFAS contaminated soil to be excavated and put in these piles, but it can still be and will still be on-site treatment, so no soil is leaving the site. Here's a small example of a IPTD pile. This one had 90 cubic yards of soil. Again, we were treating dioxins, and the target was 335 degrees Celsius. We had 9 heaters installed. You see them stick out at the end here of the pile. And 4 temperature monitoring points were basically utilized to keep track of the temperature in this pile. So in this pilot, we operated the IPTD pile for 54 days, and again the thermal the vapor treatment was by thermal oxidation. And similar story, roughly a month to get up to temperature, and from there maintaining the temperature a couple of weeks. For dioxins, we aim for at least 2 weeks, and we are looking at roughly the same time frame for PFAS. And so that's what you see here. So basically we have the temperature here, we have the dates down here, and the yellow curve here is the temperature, the average temperature in the pile. And that's actually compared to the blue curve that was our model temperature. So what this shows is that it actually heated up a little faster. And in this case, we believed it was mainly due to the fact that the soil were less moist from the beginning, and therefore less heat capacity, and therefore we were able to speed up the process a little bit. Based on the results, actually this one is just another picture of the pile itself. But based on the pilot results, that was actually very successful at this particular site. This is a site in South Korea. We moved on to full-scale application, and this is a picture of the full scale. So in this case, we were treating 10,500 cubic meters, so close to 14,000 cubic yards in this pile system. And in this particular case, we were looking to treat the dioxin contaminated soil to 100 parts per trillion, and we actually reached a goal 45 times lower than that. So again, it's all about getting the soil up to the target temperature, which also would be the case for the PFAS contaminated soil. All right, and we have done even bigger projects. This is a project in Vietnam, Da Nang Airport. Again, dioxin was what we were chasing. Each of these piles, we did 2 phases down there. Each of those piles had between 50 and 60,000 cubic yards of soil. So again, the bigger these system gets, the lower the unit cost gets as well. So this is a technology that scales very well with size in terms of the unit cost for the treatment. Looking at this, the piles in Vietnam, well, we did 2 phases, and you see there 57,000 to 60,000 cubic yards for each, 335 degrees target. In this case, we actually this was one of our first full-scale IPTD projects. So we decided for this particular application to install the heaters through the top of the pile rather than doing them horizontally. And that actually led us to install 1,254 heaters in this pile. We had monitoring points in terms of where we looked at the temperatures, and we had 56 of those. And then in the bigger the project gets, the more it makes sense to try to drag out operations a little bit. So while we were looking at maybe 2 months for the pilot scales, in this case we actually extended operation to roughly 7 months, 205 days, which basically brought down the size of the treatment equipment needed for this remedy, and the power drop, the number of infrastructure, heaters, and vapor manifolds, and so on. So, again, this concept will be targeted for the size of the project. In this case, the treatment was by cooling, phase separation, and filtration, and adsorption. Looking real quick at the temperature for the big piles here, this was for the second phase. We have the temperatures out here, and we have the days out here on the x-axis. Same story, you see the temperature get up to 100 degrees, the boiling point of water. We're sitting at that temperature for a while until all the water has boiled off, and from there we can now increase the temperature further up to. In this case, we are targeting 335, but as you can see here, we actually reached a average temperature above 500 degrees in this case. So, and this slide just shows a picture of the treatment system for this particular application. So under this roof, we had both the vapor and the liquid treatment system, and to the right in this picture, you see basically the end of the IPTD pile. So looking at, this were a few example of high temperature treatments. We've done a total of 19 projects worldwide, most of them here in North America, but also in South America, one in Europe, and then a few in Asia as well. And all that information that from a technical heating standpoint, it's the same process we will apply for the PFAS. Simply now that we have confirmed what John told, that we need to get it up to a temperature that's similar to what we do for dioxin. So the treatment system will obviously be a little different, and as John presented, we would likely go the catalyst road there to treat the vapors, but otherwise everything else is similar to what we've done many times before. Some of these projects more than 20 years ago. So wrapping this up before we will take some questions, what we have shown is that PFAS can be removed thermally, and we're looking at temperatures above 350 degrees Celsius. And from a heating standpoint, a technical standpoint, we would apply basically what we have learned on previous projects for dioxin, PCBs, pesticides, PAHs, mercury as well. We would apply that for the PFAS as well. And then now we are basically focusing on understanding the breakdown pathways and optimizing the understanding of the best vapor liquid treatment approach, and that it was actually the second round of the suitability studies. That's exactly why we initiated that catalytic focus, simply to see, okay, how do we treat these PFAS chemicals. So with that, John, I think we are ready to take some questions.
Awesome,
Yes.
Great job, guys. I've got a list of some questions here for you guys. The first one says, can you please provide some cost examples for different volumes of source material and degrees of impact?
Steffen,
Absolutely.
Yeah.
Yeah, well, I can take the first shot at it. Yes. If we're looking at an IPTD application, first of all, the bigger, the cheaper, but we are looking at, and we know that from the other full-scale projects, we're looking at, the big ones, we're looking at roughly $350 per cubic yards, but the smaller they get, we get up around $450, $500 per cubic yards typically. Obviously, it does depend on also on what kind of treatment approach we take, but that's roughly where we think we are, what we have seen on previous projects, and we believe that's where the PFAS full-scale cost also will end.
Yeah, I'd just like to add a little bit to that. Those costs represent total treatment, so we're not creating a residue or something else that has to be sent off to a landfill or put in an underground injection well. This is basically eliminating your liability associated with the PFAS contamination.
Good point, yeah.
Great. Second question here. From the PFAS 101 course, what power load and source supply heated the wells to in situ treat? What was the spacing, area treated? Lastly, time to be effective?
Yeah,
we covered a lot of this.
We did cover a bunch of that, but let me kick it off. I think we had another question on power supply, so maybe we can handle these two at once. And Steffen, you can jump in here a little bit. But typically, the spacing we would use for in situ applications or piles, really, if we do it horizontally, it's kind of just turn the problem on its side, is in the range of 10 to 12 feet between the heaters. And as Steffen said, that really depends on how much time we want to spend, because the shorter the spacing between the heaters, the more energy we can put in over a period of time, the quicker it will heat up. Sometimes we want to do that for a small volume, but for large volumes, we really find the economic scale to be where we would push 10 feet or maybe a little bit more, for those larger scales, and heat up a little bit more slowly.
Great.
Yeah. No, the only thing maybe to add to that is, we typically aim for a heater input in the order of 300, 320 watts per foot of our heater elements. But what happens is, as the soil, the sediment, sludge, whatever we treat, as it dries out, the thermal conductivity decreases, and we end up typically to have to decrease that power input. So, anywhere between 200 and I would say 225 to 300 watts per foot is what our actual heaters puts out. And as John said, the closer we put the heaters, the faster the project will be, but also more infrastructure, more higher power drop, and so on. So we have kind of the heater spacing is kind of the tool we use to optimize the project and basically bring the cost down, try to find the cost sweet spot.
Yeah, and Nate, before we move on to the next one, I noticed here we had some similar themes here, which is, this seems energy intensive. How much, is it possible? I mean, what kind of power drops are required? Is this even available or doable? We've been doing, thermal remediation projects for a long time. There is, for most sites, most applications, all of these, there's available power on the grid. We're not talking about, a power supply for a city. We're talking about something that might be similar to a manufacturing facility, something in the range of 500 kW up to several megawatts of power. That's typically available on power grids. These are not, extraordinary, power supplies or transformers or demands that have to be specially engineered and designed. Again, it depends on where you are. If you're out in the middle of nowhere, you might not have the power available that you need. But typically in urban settings or any of the settings that we've been talking about here, there's available power. I don't know, Steffen, if you had anything you wanted to add to that.
No, I totally agree. We have turned down project in the woods of Alaska, definitely because of this. But a lot of these brownfields, development sites, they already have power there. They need power for the future development. And actually earlier this week, we're looking at a site where the power drop they already had in mind for this site was what we needed was less than 2% of that power drop. That was a big power drop though for this particular site, but still, typically we sometimes do end having to bring power in from few sides of a site. We did a project in Teterboro, New Jersey, where we had a total of 4 separate power drops, but it all depends on the size of a project and do we elect to do it in a phased approach to bring down the total power drop and so on. Yeah.
I think the key takeaway is that what we're doing here doesn't require extraordinary power. It requires power drops and supplies that are typically available for manufacturing facilities. So if you're moving a warehouse or manufacturing facility or building one in one of these areas, or as Steffen said, a brownfield redevelopment, that grid, that infrastructure is already in place to provide the amount of power we need.
Sounds good. All right, let's move on to another question. Have you noticed the transformation of telomers during thermal desorption projects?
Ooh, I am so glad we have Allison on the line. Allison, you still there?
I am still here. And I guess in terms of the work that we have done on the bench scale, we have not seen that yet. We have seen a few small detections of those compounds in what is most likely just sort of background. But since for especially the second phase of the work that John described, where we were focusing on spiking in one compound, PFOS, we were really trying to keep the chemistry simple. One thing that was sort of a conclusion that we were all instantly made aware of is that the chemistry is not simple, even with when you're only spiking in one compound. But we did not see those compounds in the work that we've done. So it certainly will be interesting to see that on a full scale with a different suite of PFAS compounds. But for the work we've done, we haven't observed that.
Yeah, you could see this is the results from the second lab analysis, and these are the fluorotelomers here. Yeah, we didn't pick up any in background, and we didn't see any at these detection limits, post thermal. So obviously this
we had a couple just super low level hits in one of the matrices, like in the condensate or something. But again, they were all J flagged, estimated below the reporting limits. So they were very, very low concentrations, potentially just sort of background noise.
Great. Let's see. Well, we have Allison. I think here's another one for her. Which method do you use to detect PFAS? How much reliability does this method have?
Sure. As a chemist, for me, it's really exciting because this is a quickly evolving field. There's new methods being developed, new compounds being added to compound lists for these methods. So certainly it is a little bit of a moving target to keep up with the latest technology of what's available. For our bench scale work, we certainly both times around used the most current methods that were available. In both instances, we worked with Eurofins, who is one of the laboratories out there that is at the forefront of this work. Pretty much when we're looking at the targeted PFAS compounds, there are different analyte lists anywhere from, say, 30. Some of them can report up to, I think, 75 compounds. That's including some of these precursor compounds. But they are all mostly focused on an LC-MS-MS analysis, which is liquid chromatography with dual tandem mass spec. And that analysis is very focused on the semi-volatile, PFAS compounds, which is the regulated compounds that, EPA has recently put out RSLs for, etc. What John mentioned with our second phase of the bench scale study that we just completed, we also did this combustion ion chromatography approach. And there's a few different ways that can be executed. There's no official promulgated methods for that yet, I believe. So a lot of the laboratories sort of have their own internal standard operating procedures. And so that's what we followed there. But to answer the question, do we feel confident that we're analyzing them to the best of our ability? Yes, but it definitely is important to sort of work with your analytical laboratory and make sure that you talk through all the different options that are available. I know for our bench scale study, we had several very long conversations with the laboratory about what our objectives were, what we expected to see, how we were going to use the data, etc. So I would stress that that's a really important conversation for anyone to have up front before they're starting any sort of a PFAS project.
Yeah, I'd just like to add that what we're doing here is very different than what we traditionally do. So we're looking at 30, 35 target PFAS compounds out of thousands. So the question really is, if the EPA is regulating, or you have to clean up to one or two of those 35 compounds, or one or two of those thousands of compounds, and you have a lab method or an approach that shows that you get destruction removal, you meet that goal. Would you typically want to look for all these other compounds? Do you care? Does the EPA care? Are you regulated for that? What we're trying to do here, and the reason we made it complicated, and fortunately fortunately, we had Allison on our team to help us sort through this, is it wasn't enough just to say, okay, the PFAS goes away, we're good, we're done. We wanted to know more specifically, what is the fate of that PFAS? Is it mineralized? Does it transform into something else that could show up on an analyte list and regulated in the future? That's what we're doing. And what Allison was just describing is that we're really pushing up against the limits or the ability of labs to sample and analyze, extract and analyze for some of these compounds. But we do think in our round 2 of our lab studies, we were able to track the fluorine associated with background as well as our PFAS that we spiked in through the system. And we have some insights as to what form that, what happened to it, the fate of that. So, and that actually brings me to one of the questions here that we had right in, which is there much toxicity information for volatilized PFAS? And I'm not a toxicologist. And again, these standards and regulations are being developed, as we talk here. But I would say that, is there a risk that while we're thermally treating it, that leaks could be, highly toxic? That's always a question and a concern at any of our sites, whether we're treating TCE, vinyl chloride, or dioxins. And as Steffen said, we've done a lot of dioxin work. A couple things to keep in mind: that these results show that we get volatilization of something. We're not sure exactly what it is because we don't have sampling and analytical methods to say exactly what it is. But we think could be HF leaving the system. It could be degradation products of these PFAS, that are compounds that don't show up on the target list. But at the end of the day, these systems that we run, whether it's for dioxins, PCBs, or other highly toxic chemicals, they're designed and constructed to minimize or eliminate leaks. Everything is kept under vacuum from the well field all the way through the treatment system to the exhaust. So if there's leaks, it's leaks coming into the system, not leaving the system. And I don't know, Allison, Steffen, if you have anything to add on that, but we don't know. I think is probably the we know there isn't a lot of toxicity information on volatilized PFAS, but we're pretty confident that we can design and construct and operate systems that would address any of those concerns.
All right, here was one question. I think it's perfect for this slide. How long was the waiting time after PFAS spiking into the sediments before the thermal testing?
Ooh, take it away, Allison.
The system was spiked and sort of agitated just to ensure that it was well mixed in the system. As John described, and with any of these sort of high temperature projects, you're going through a boil off phase. So there was, water also added to the clean sand that was then spiked with PFAS. We did that. So again, we were aiming to try to close the mass balance. So we added a lot of water to the system such that we would have enough condensate generated in the bench scale, in that small scale setting, to then have enough sufficient volume to do all the analyses that we wanted to do, right? So we sort of had to construct it with our end goals in mind of all the analytical we wanted to do, and then sort of had to back calculate, well, okay, how much water do we need in the system? So during that, we start off in that boil off phase. That's maybe a few days worth of period of time at the most. And then, as we discussed, we held the 350 degrees C temperature for 7 days. So, start to finish, each one of those runs was about 9 or 10 days. And then at the conclusion of that, the heat was turned off and the system was allowed to cool. And then from there, the samples were sent off for analysis, right? So, you're talking a week start to finish, a little over 10 days.
Great. Here's a more general one. What is the target source zone of thermal treatment, aquifer or vadose?
Steffen, you want to do that one?
Yeah, I can start out there. Well, we need to get to temperatures above the boiling point. So we basically, if there's water present, we need to control it. And in reality, that is very different in the aquifer. So this technology, is targeted source zones, preferable in the vadose zone, or if not in the vadose zone, then at a location where we can dig up the source zone from below the water table and put it in a pile ex situ on site. So this is definitely not a groundwater plume technology. It's a source zone technology. And we need to be able to control the water. So if it's in situ, we need to pump down the water. That's very difficult. So honestly, on the first full-scale projects here, we would go for a vadose zone, or basically to dig up the soil, put it in a pile, treat it in a pile ex situ above the water table.
Yep, makes sense. All right, one final question, should be a quick one. What is the long-term impact of heating soils to these high temperatures? Do microorganisms, etc., eventually return?
Well, yeah, I mean, in situ they do. I mean, heating to these high temperatures, 350, 400 degrees C, 500 C, we're going to get, sterilization of a lot of these microorganisms at those temperatures. But natural systems are incredibly dynamic. We have seen, rebound at in situ applications. I don't think we've ever really looked at soil from a pile as to how quickly organisms repopulate, but groundwater flux, vapor movement, air movement through the soil pile will quickly repopulate. We see usually very robust rebound of microbial populations in soil that we've heated to 100 degrees C or to these temperatures. And one of the reasons for that is that at these temperatures, especially at these high temperatures, we're liberating quite a bit of organic carbon. So we're making that available to the organisms. So they're very happy to come back in and repopulate these piles and stuff. I don't see any particular reason why there wouldn't be a robust microbial population, either naturally or through amendments post thermal treatment.
Great.
There has I would agree with that. And there has, 15 years ago, even 20 years ago, there was a lot of research, right, when thermal basically was starting to be, more accepted in the industry. And there are papers out there that describe this. One of them being by Anne Fries, a student from the Danish Technical University, that basically looked at steam, looked at ERH, and looked at the repopulation. And exactly what you said, John, actually this typically will be a bloom after thermal, simply because, there will be a period of time where the temperature in the cool-off phase is really good for a bio bloom. So
Excellent. And that's the last question. So I'm just going to get started with some closing remarks here. So first off, thank you, John, Steffen, and Allison, and for everyone in our audience for taking time out of your busy schedules to attend today's webinar. We really hope you enjoyed today's session. A recording will be circulated to all those in attendance within a week. Our next webinar is going to be on October 26th, and it's titled More Money, More Delays, How to Limit Cost Overruns and Remediation Problems with New Technology and Approaches. You can register for that one at cascade-emv.com/resources/webinars. And as you log off today, you will receive a very brief survey. We thank you in advance for providing feedback on today's session. we really do read every survey in an attempt to make our webinars even better. So with that, thank you again, everyone, and we'll see you next time.
Yes,
Thank you all.
Thank you for your time. Bye.